Today's a fantastic day because today we're going to be doing the derivatives of trigonometric functions. See, trigonometric functions are very wonderful and beautiful functions, and they have a special place in my heart. Indeed, the very first class I ever taught was trigonometry, and that was let's say a long time ago. And why do we care about trigonometric functions? Well, if you think about what trigonometric functions are, oftentimes you think of the sine function, which does something like this, where you're going up and down. But the nice thing about trigonometric functions is they're functions which are periodic. So any type of phenomenon which has a periodic element to it, you oftentimes will use a trigonometric function to model. For example, if you have a spring that's doing some up and down motion, that periodic behavior of the spring moving up and down, that can be modeled using trigonometric functions, or at least certainly trigonometric functions will show up somewhere. So it's nice to know what are the derivatives of trigonometric functions so we can start talking about things, well, how do things change when trigonometric functions are involved? So that's our goal. So let's get started. So first off, we have to have some basic facts. Now these are things which some of them we've talked about and some of them come from our trigonometry class. So what are things that we've talked about? Well, no surprise, limits are going to be involved. So the limit as h goes to 0 of sine of h over h is 1. Really important limit. And this limit is one that bridges the world of trigonometry with the world of algebra. So it's not surprising that we're going to need it. And one of the things that we actually showed in our practice, and this is important, is that the limit as h goes to 0 of cosine of h minus 1 over h is equal to 0. All right, so those are our two limits. The other element we need is how do we break up addition in the sine and the cosine function. So sine of a plus b is sine a cosine b plus sine b cosine a. Cosine a plus b is cosine a cosine b minus sine a sine b. All right, so those are some basic facts that we'll need. Okay, so let's assume those for now. Certainly the limits we're good with, and we'll just accept this for right now. And let's proceed. So there's two important trigonometric functions that we want to start with. And the first one is the sine. And what's the derivative of the sine? The answer is cosine. Aha! Okay, so how does that work? Well, whenever you want to establish a fact about derivatives, we always say, let's go into the definition. So into the definition we go. So my function is sine. So if I want to take the derivative, that's what our d dx stands for, of sine, we say, okay, here's our function. Limit as h goes to 0, sine of x plus h minus sine x all over h. Now, we say, hey, I really want to make this sine of x plus h look more like sine of x. So I'd like to get rid of the plus on the inside. You see, we want to have these be comparable. So the way we do it is we say, let's use our little trig fact where we have sine of like something plus something is this expression. And so that's what happens. I'm going to take the sine of x plus h. That's sine x cosine h plus sine h cosine x. Good. All right. There's still the minus sine x on the end, all over h. Now, what we do is we start grouping. Well, how do we group? You see, there's two pieces here that involve sine x. So we're going to put those together. So you get a sine of x, cosine of h, minus 1. Okay, so sine x times cosine h minus 1. What else do you have? Well, you have a cosine of x and a sine h. And then, of course, there's an over h downstairs. Now, let's see what happens. Well, we can kind of see what's going to happen. You see the sine x and the cosine x, these pieces here, they're not changing as h goes to 0. So the question is, what happens to these other pieces? And that's why we needed our limits. Sine h over h, as h goes to 0 goes to 1. So you end up with cosine of x times 1. Sine x times cosine h minus 1 over h goes to 0. So you end up with 0. And therefore, the first part is gone, and we're left with cosine x. All right, good. Now, before we go to our next one, you can kind of guess what the next one is going to be, I want to just point out that this graph right here, this is the graph of sine of x. And this other graph is the graph of cosine x. And we should actually say, is it reasonable that when we have, hey, the derivative of sine is cosine? So let's take a look and see what's happening here. So one of the things you often look for is you're saying, what's the behavior? So for instance, here at 0, we see, oh, there's a tangent line. It has positive slope. So it looks like about the line y equals x. And if you've been doing the practice, you see, yeah, it is like the line y equals x. So that's a slope of about 1. Okay, so that's good. Notice this point right there, the very top. What do you see about that tangent line? It's a flat tangent line. Flat tangent line means the derivative is 0. So if the derivative is 0, then when I look at the derivative function, I should have 0. All right. And you can even see as the behavior as you go, your positive slope, and then you're sort of heading towards 0. And then what happens? You start to go negative, and then you hit, roughly it looks like the steepest point is right here. Well, all right, that's a very steep negative. And then you come over to here, and it's 0 again. And then you're back to 0. So we can see that if you think about what's happening to your slopes of your tangent lines, we can get a sense this is what the derivative ought to look like. And we can say, yeah, cosine x is behaving like what the derivative of sine x should be, where the tangent lines to sine are going in an uphill direction, the cosine function is positive, where the tangent lines for sines are going in a downhill direction. The values for cosine are negative. Okay, good. All right, so really simple. The derivative of sine is cosine. Well, so the reasonable thing to do is, let's talk about the derivative of cosine. All right, any guess? Let's find out. Well, of course, we're not going to guess. We're going to get the answer. So, what's the derivative of cosine? So the derivative of cosine is negative sine. So close. Man, this negative right here, so many people get tripped up by the fact that there's a negative there. Now, not necessarily that they're like, it's shocking, but it's easy to lose track of it. So this is the one where you got to pay attention. So be careful. The derivative of cosine introduces a negative into the expression. All right, so what do? Well, we do the same logic. So we're taking the derivative of cosine, all right, cosine of x plus h minus cosine x over h. Now, what can you do? Well, cosine of x plus h, break it up. Cosine x cosine h minus sine x sine h minus cosine x over h. And now we go do a similar thing, which is we group and we put things together. So for instance, we see the cosine and the cosine are going to go together. So there's cosine, cosine, then there's the cosine of h, and then minus 1 because we grabbed everything except the minus sign all over h. Then here you got the sine of x and sine h over h. Again, things go to 0 and to 1, and the minus is coming from this part right there. See, there's the minus, and so we end up with minus sine of x. So the derivative of cosine is negative sine. All right, well, again, let's think about the pictures. So this curve, this first curve, is the cosine curve. And this second curve is negative sine. And now we can, again, think about what's happening. So at 0, we have that flat tangent line. Well, that should correspond to where the derivative is 0. All right, that's good. And then we're negative. So for instance, here, we have a fairly, relatively speaking, negative slope. So it's a fairly negative where the derivative is. Over here, again, we can see the derivative is 0. So lo and behold, we're going to 0. And you can see that if you think about what the behavior is, we are 0. Then we're going down. That means negative derivative. Then we sort of like get sort of shallower as we're going down. So we're sort of steeper and steeper, then shallower and shallower. We're back to a flat slope for the tangent line, back to 0. So you can start building intuition. Hey, if I know something about the shape of the function, I can get some idea about the shape of the derivative. I think about tangent lines. Are they positive? Are they negative? Are they zero? How is the behavior? And if I understand these things, I can piece them together. Then I can start to understand how the derivative should look like and get a sense of the right behavior. All right, well, that's two trigonometric functions, but there's more. Now you might say, okay, are we going to do a lot more limits? And the answer is no. That's the end of our limits as far as trigonometric functions are concerned, because what happens is the remaining trigonometric functions can be expressed as proper combinations of sines and cosines, which means once we know how to take the derivatives for sines and cosines, we can use that combined with our rules to figure out the derivatives of the other terms. So let's talk about our other derivatives. Okay, so here we go. We'll just put them all up at the same time. So we have the tangent, that's sine over cosine, which means we're going to use the quotient rule because there's a sine over a cosine. So we're going to take the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Well, you get cosine squared minus minus makes plus sine squared. Cosine squared plus sine squared is 1. Aha! 1 over cosine squared. Now, 1 over cosine is secant, so 1 over cosine squared, secant squared. All right, how about for cotangent? Well, cotangent, it's the opposite. It's cosine over sine. So bottom times the root of the top minus the top times the root of the bottom. Well, now you get a minus sine squared minus cosine squared. So it's going to be minus 1 over sine squared. So minus 1 over sine squared. Well, 1 over sine is a cosecant. So 1 over sine squared is cosecant squared. All right, how about secant? Well, so secant is 1 over cosine. So now we can use the reciprocal rule. So we take the negative of the derivative on the bottom all over the bottom squared. So we end up with a sine of x over cosine of x squared. Well, we're going to break that apart. So we're going to have a 1 over cosine and a sine over cosine. And what do we end up with? 1 over cosine is secant, sine over cosine is tangent. So the derivative of secant is secant tangent. The derivative of cosecant, 1 over sine, and then we end up with, again, reciprocal rule, negative derivative of the bottom over the bottom squared. Again, break it up, negative 1 over sine, cosine over sine, so that's a cosecant and a cotangent, and you get minus cosecant cotangent. All right, so there's our rules. Now, one of the things you might ask the question about, well, which ones do you need to know? And here are the ones you need to know. You definitely need to know the derivative of sine, so we'll throw this one in. The derivative of sine is cosine, and you definitely need to know the derivative of cosine, which is negative sine. These are just your bread and butter. And then you need to know the derivative of tangent of x is secant squared, and the derivative of secant x is secant x tangent x. In other words, those ones over there, those are the ones you need to be focusing your energy on. Memorize those. Now, you might be saying, wait a second, Steve, you're showing a lot of bias here. Why do you not care so much about the cotangent and the cosecant? Well, you can memorize those, but we tend not to use them very much. Now, you might wonder, why don't you use them so much? And this is my opinion about why they don't get used so much. Not because we're somehow biased against the word co, but because of the fact that there's negatives that show up inside their derivatives. And oftentimes mathematicians have learned over the years that every time we introduce something like a negative, it's easy to forget it. And so if they like to try to say, let me try to avoid things which introduce negatives. That's why I think that we like to avoid the cotangent and the cosecant. I want to point something out, though. This is kind of, if you can see the spirit of it, it can help you remember how to memorize the derivative of tangent and cotangent sort of go together. Notice, when we talked about the derivative of sine, it was cosine. And the derivative of cosine was negative sine. Now what happened? Two things happened. We flipped the and we changed the sign. You see? So this was positive, this was negative. Cosine, sine. So we got rid of the and then we put in a negative. Now, check it out. From tangent to cotangent, see, secant, cosecant. So you flip the So there's secant, there's cosecant, and you put in the negative. All right, how about secant versus cosecant? All right, well, secant, cosecant, there's a flip of a tangent, cotangent, flip of a positive, negative. So in some sense, they do follow a nice pattern. So if you know what the derivative of tangent is, you're like, oh, for the derivative of cotangent, I throw in a negative and I put a somewhere. And similarly for secant, and so forth and so on. So that's how you can memorize it. Okay, good. Well, those are our trigonometric functions. And now we have them, right? And now we can start exploring the calculus of them. Well, you might be thinking, you know what? There is still one piece. Is it really the case that sine of A plus B is sine A cosine B plus sine B cosine A? And let's just take a couple of minutes just for fun and rederive it. So this is not really a calculus part. We're just wanting to talk about a trig part. But like I said, trig is near and dear to my heart. So we're going to do a very special case. So first off, a little fact here. We'll just draw ourselves a triangle, and it's not going to be any kind of triangle. Of course, it's going to be the right kind of triangle because it's trigonometry. And suppose I had theta, and let's suppose I had, this was my length of my hypotenuse. Well, we'll call it h for hypotenuse for right now. Okay, what can I say about this opposite side? Well, this opposite side, call it the opposite temporarily, what's true? Well, I can relate the opposite and the hypotenuse together by looking at the ratio called sine. So sine of theta is the opposite side over the hypotenuse. So that means that really this opposite side is h sine theta. Now how about this adjacent side? Well, the adjacent side, that can be related between h and theta by the cosine. So cosine theta is the adjacent over the hypotenuse, which tells us that the adjacent side is h cosine theta. All right, so we can do what's called projection. Now, here we go. And let's draw ourselves a picture. So, we're going to make a little picture here. Let's put our angle A inside there. And now, what comes next is we're going to draw another triangle. This, by the way, is a right triangle. Here we go. You can see, there it is. It's right. All right. Now, we're going to draw another right triangle. And this angle here is B. It's not A, it's B. All right. And throw in one more triangle here. And here we go. And this is also a right triangle. All right. Now, let's make a note of a couple things. If this angle is A, this angle is the complementary angle to A. Because all three, in other words, it's like 90 degrees minus A or pi half minus A, depending upon what kind of angle measurement you're using. This angle is the complement to that angle, because notice there you have 180 degrees here. There's a 90 degree angle. What does that mean? That means that this angle here in the corner is A. All right. Now, here we go. I'm going to tell you that this side has length 1. And the goal is mark down all the lengths in this picture. So we're going to do it. So I can start with this triangle And I'm going to use this fact. Here, h is 1. So the opposite side, this side over here, this has length sine b, because it's the hypotenuse times the sine of the angle. This length down here has length cosine b. All right, now, what else do we have? Well, let's do this triangle downstairs. So the hypotenuse has length cosine b. This angle is a. So this total length here, that's cosine a cosine b. This length on the side is what? Well, that would be cosine, well, I'll write it as sine a cosine b, right? Because the hypotenuse is cosine b, so I multiply the hypotenuse times the sine of the angle, and the angle is a. All right, now let's come up to this triangle. So first off, we'll do this piece right here. What is that? Well, it's the adjacent side to a. Here's my hypotenuse. So adjacent would be cosine a sine b. The cosine of the angle times the length of the hypotenuse. One more length, and that's this part up here. So it's the opposite side. So here, it's going to use the sine of the angle a times the length of the hypotenuse. So this is sine of a sine of b. All right, now, one last bit of, and then we're going to be done. One more triangle. And you're like, what? Another triangle? Steve, you crazy man. How many triangles can you put into one picture? As many as I need. And in this case, I need one more triangle. Now, what's this angle in the corner? It's a plus b. What's the length up and down? Well, I know the hypotenuse is 1, so this is sine of a plus b. What's this length here? Well, it's the adjacent, and I know that this length is 1, so that's the cosine of a plus b. All right, are you ready? Here we go. Check it out. Sine of a plus b. This length is equal to these two lengths together, because this is a rectangle here. All these corners are right angles. Since it's a rectangle, these two lengths are the same. So sine of a plus b, sine a cosine b, cosine a sine b. That's exactly what we said, and we add them together. Now, where's cosine of a plus b? It's this length downstairs. How do you find it? Well, take this longer length, cosine a cosine b, subtract off this shorter length, subtract sine a sine b. And it works. It's beautiful. A beautiful argument. I love this argument. Man, boy, do I miss teaching trig. It's a beautiful subject. Okay. All right. Well, that was a little bit of a side for people who needed a short break from calculus. Of course, we should get back into calculus and do our practice. So let's get back to it.